Well, today we are dealing with wood as a material. We'll be looking at the properties of wood and some of the products that are available for building with. And so later on, we'll start dealing with other aspects of wood, heavy timber, actually framing, but those will be different chapters. But here we're just looking at the material called wood. So the first thing in this picture, this cross-section of a log, something we all learned when we were young, is that you can figure out how many years old a tree is by counting its rings. So how and why does a tree get rings like that? Well, it turns out that in the spring of the year, there's a lot of growth. And that's true with trees too. So they do most of their growing, the fast growing, during the springtime, and that's the light-colored wood. And then the rest of the year, it slows down, and you end up with the dark rings for that period. So let's kind of move on to the next page, and I've got some things. So yes, we're looking at trees themselves, of course, but if you look at this log here, in this another section like this, there's a bunch of terms here, and they're all kind of interesting. What I really care about you understanding is really the concept of these annular growth rings result from differences in the rate of tree growth throughout the year, and you get a more dense density, a tighter density of wood in the dark rings. That wood is stronger or tougher to drill through or cut through than the pulpy material that grows when it's growing fast in the spring. So now, maybe the most important thing on this page is the last bullet over underneath the log here. It says, moist climates yield faster growing trees. A faster growing tree yields weaker lumber that can carry less load at lesser spans. Or the opposite is true, that you could say in a dry climate, the same tree growing in a dry climate compared to a moist climate is going to take many more years to get to be, let's say, a 12-inch diameter log than would a tree growing in a moist climate where things are going to grow a lot faster. And so what happens is you end up with a lot more pulpy material between the rings. There'll be wider rings, whereas in a drier climate, the rings will be closer together because there'll be less pulpy material because there was a lot less growth going along each year. And so it also means that a 12-inch log in a moist climate will be younger than a 12-inch diameter log in a dry climate with the same species of wood. So what does that all matter? It's because there are actually load tables that are different depending on whether it's a moist growing tree, a moist climate, or an arid climate, a dry climate, because those logs that were grown in a drier climate are going to be stronger. They'll span greater distances. They also took a lot more years to get there, so they're older. So it's another reason. But I guess the point here being that that's why there are separate tables for load tables that engineers use when they're designing spans of wood. It also is why another issue is that when the wood is moist, when you freshly first cut it down, the tree has a lot of moisture in it, and so the log actually is bigger than it will be in diameter, a bigger diameter, or there's more, it's plumper between those layers than it will be after it's had a chance to season or dry out. And so if you build a log cabin with fresh green logs, and let's say you've got 10-foot high walls, that's pretty good, stacking those green logs up, well, over time as the wood dries out, once it has a chance to dry out, and the wood will shrink. And across the grain, across the diameter of that log, on average, you lose about 10% of the diameter. So a 10-inch diameter log becomes a 9-inch diameter log. Doesn't sound like much, but if you're talking about a 10-foot tall wall of logs in your log cabin, well, it's going to be a 9-foot tall wall after a while. And so if you start installing windows, the openings are shrinking and exploding windows, or doors aren't going to fit either. And so we don't build that way. We don't build with green lumber, hardly ever. We typically use seasoned lumber that's had a chance to cure, to dry out. Okay, so let's kind of move along a little bit. There's also softwoods and hardwoods. So compared to hardwoods, the softwoods are a simpler cell structure. Well, the first basic thing is, what's a softwood compared to a hardwood? Well, the cone-bearing trees, or the ones with pine needles, evergreen trees, those are all softwoods. So things like pine and fir, but it also includes, trees like that are made with cypress. Though that's an oddball tree in that it's still a cone-bearing tree. Sometimes you have to just squint a little bit to find the cones. So we call them cone-bearing or coniferous, not carnivorous. That would be a meat-eating tree. I would not like to meet one of those ever, especially in a dark alley. But relatively simple structure to the cells compared to the hardwood trees, which are leaf-bearing, broadleaf trees. So generally the plain figure that you see of the grain is a simpler structure also. But anyways, softwoods are easy to cut through and work with, and so it makes for a great product to frame up houses with. And so our framing of houses is all typically with softwoods. A lot of pine, spruce, and fir. So, mostly originating from North American forests, the fast-growing, plentiful, relatively inexpensive trees. They're soft and easy to work with. Structural wood products, finish and trim, shingles and siding. Because, for instance, cedar trees and redwood trees, those are evergreen trees. Those are cone-bearing trees or carnivorous trees. So those are examples of softwood. However, not all softwoods are just plain and simply soft. There are some softwoods that are harder than some hardwoods. So Douglas fir can often be harder than quite a few different hardwoods. It kind of depends on the sample and circumstances. But in general, a Douglas fir would be harder than a poplar tree. A poplar wood is a fairly soft hardwood. So that would be a good example. So it's not a perfect statement to just say softwoods are soft and hardwoods are hard. But in general, you'll have a much harder time with most hardwoods when it goes to ripping along them or cutting them or shooting nails. It's hard to shoot a framing nail with a nail gun or even with a good old-fashioned hammer into oak or ash or pecan or mahogany. These are hardwoods that are much tougher to run fasteners through. We typically have to pre-drill those holes. Okay, so hardwoods from broadleaf, the deciduous trees. So you might remember that word from many years ago. Well, deciduous trees are any tree with a big broad leaf, so as opposed to pine needles or such. So they're a more complex structure to the cells, often more interesting figure and its shape and such. So on the top we've got a sample of walnut. Now on the bottom we've got red oak, and you see that the wood grain pattern is different in there. So harvested from around the world, hardwoods are all over the place. However, they are slower growing generally, more expensive than softwoods because they're slower growing, partly, and also because they're not used for the same purpose. You don't use hardwoods to make 2x4s. It just doesn't happen. I mean, it doesn't mean you couldn't, but it's a lot of work and it's just not practical. And here's the thing, pine trees, in many, many cases out in the wild, those trees will grow straight and true, which make them great for nice, straight, long pieces of lumber. Whereas plenty of hardwoods will be twisty and bent up and gnarly and are not. There's some hardwood trees that can be straight, but it's more of a problem there. So it's denser material with greater variety of colors and figure, and so it do make for interesting furniture when they're stained and such, because the hardwood just has a lot of interesting character in its in its colors and stuff. So it's generally used for. Oh, and because it's harder, it's harder to rub through it or scratch it. So it makes a lot of sense to use hardwood for flooring as opposed to softwood, because the hardwood won't scratch as much as you walk over it. So an area that's going to wear, you're going to wear a path through somewhere, you're going to do that more quickly in a softwood like a pine, whereas a hardwood like an oak will be very wear resistant, so it works better for flooring. And we use it for a lot of cabinet and trim, crown molding and such things like that in furniture. Okay, so when it comes to certified wood, that's a term that's important, especially more and more every year. How responsibly the forest is managed that you harvest any of this wood from matters a lot more, because if you cut down the rainforest, they don't grow back. If you cut down huge forests of pine even, and spruce and fir in the northwest of this country where a lot of that is, you're going to find that it doesn't grow back. Just because you mow it all down, it's not going to grow back. You've got to be more responsible. And so we found that it's better if you don't take the whole forest down, but instead select trees and leave some behind to hold the soil together and to keep the ecosystem going. And when you talk about hardwoods, it's even more important because they take longer to grow and it's even more complex. So certified wood, there's a program that's part of LEED. Back in chapter 1, we were talking about LEED certifications. Well, certified wood is one of the aspects of LEED, of a LEED project, in what you've got to show documentation that you've purchased this wood from a certified, responsibly grown, harvested forest. Okay, so here's a map of certified wood. It's pretty old here, so I don't know. I guess I should try to see if I can find a digital version. I know I've got the textbook, the newer version of the textbook that I base this course on, that I could go and get. But it would be scanned. I don't know. It might still be better than this. I'll see. But it basically shows certain parts of the world that are doing a better job of responsibly managing their forest. And so green normally is considered good, but it's really only mediocre on the scale. If you look over there, the ones that do the best job of responsibly managing their forest are those darker colors, darker green and darker hues, and they look like they're almost turning brown and stuff in here. So it shows that that's one issue, but that's just looking at it in a general space. Within any local region, there's responsibly grown forests, so you can still get from any of these most of these parts of the world, you can find responsibly grown lumber. So this is a stack of responsibly grown lumber. It's the Forest Stewardship Council, the FSC. It's the only certifying organization that I know of that's recognized by LEED for LEED certification. And so basically, yes, there's a stamp on the side of that stack of lumber, but there also would be a certificate that would be included with the shipping of that stack of lumber. That would help prove it. That's the kind of documentation you need when you're running a LEED project like that. So let's look at lumber in general now. Looking at a bunch of this stuff stacked up. It needs to be stacked up well like this and bound to help keep it straight. And so that is important, because as it dries out, it can tend to twist and change shape. So first of all, a couple of terms to learn about. When you can kind of see that this is the remnants of a log, you can kind of see the round corners of the centerpiece. If the piece was cut right through the center of the log, like you see on the left-hand side, that's considered to be quarter-sawn lumber. It's more dimensionally stable, and the rings are mostly running in straight lines through the board, which helps to make it dimensionally stable. It's not going to twist as much. It's not going to shrink weirdly either. Whereas over on the right-hand side, we've got plain-sawn lumber, where it's been cut from the outside of the log. And even if they're the same dimension of wood boards, the one on the right-hand side that's been cut from the outside of the log, the plain-sawn lumber board, will tend to shrink in a strange way. You'll get kind of a cupping on the board, because what happens is you get more shrinkage on the outside of the log than you do on the inside. And so the part of the wood that's closer to the outside will shrink more, and so it will tend to cup in this case, so the part that's down right now will end up in the center, will tend to lift up as it dries. Another characteristic thing about plain sawn lumber are the V shapes that you see in the patterns of the lumber, because the growth rings aren't perfectly in line with where we're cutting, and so you tend to see those kind of patterns show up in plain sawn lumber. So let's look at a couple other pictures here. Quarter sawn lumber up at the top. If you're looking at the edge of the lumber, well, actually, let's look at the big log first over on the right. You can see if you're cutting, so when they call it quarter sawn, because big logs, they would literally slice into quarters and then rotate them so that they can slice perpendicular to the wood grain, so they can end up with those lines in there. And then with plain sawn, they don't worry about it, and then you're going to end up getting lots of parallel lumber. If you're looking down the very end of the board, you see the pattern that we're talking about. And that same pattern shows up over on the right-hand side. And so quarter sawn, you've got the lines all pretty close together, running parallel to each other, I guess you say, but it means that all the short lines are showing up on the flat side of the board, and you see a whole bunch of, you see tight grain. And so when we're building furniture, stuff that's going to be seen, if it's going to be painted, no one cares. But if it's going to be seen because it's stained and as furniture, then that grain matters as far as the look, just for the stain. It looks entirely different when you look at the plain sawn. In fact, if you put those two pieces together in the same piece of furniture and stain them, they'll tend to look like they're totally different species that have nothing to do with each other, even though they came from the same tree. So that rift sawn thing is kind of a combination thing. We won't worry about that. And then, but the flat sawn or plain sawn, it means the same thing. Where you've got kind of the lines are running in this long run. I mean, you're looking at the end of the board. You can see how the lines are kind of running through, and so that really the short lines are showing up on the edge of the board instead of the wide, flat surface of the board. So let me see, what can I show you? Here's some plain sawn lumber, and you can kind of see the V's showing up in the lumber. We've got red oak and white oak, so they're both oak trees here. So you tend to get more distortion of the board. So we call, again, plain sawn can be flat sawn or flat grain. Oh yeah, one more thing. Let me back up to this page. Notice on the left-hand side it says quarter sawed, rift sawed, flat sawed. So it sounds like somebody's having grammatical issues here, but actually this is some of the lingo that goes on in the lumber business. And so, you know, they don't all have master's degrees, but also it's just what happens is when something gets used in language enough times, eventually it becomes correct regardless. So it is a thing. I can't say it. It bothers me a little bit too much, but I'll say it sometimes, I guess. But yeah, so maybe more grammatically correct for your English teacher. You wouldn't want to try that with your English paper, but because it probably wouldn't fly. But it is a truth in the industry, and so don't go and correct your boss or whatever if you start talking about quarter-sawed lumber. Anyways, quarter-sawn I think is better, but still, that's it. It is still a thing. Okay, back to the plain sawn lumber. We were looking at the characteristic V's. So let's go to look at another thing. This is quarter-sawn lumber, and there's really no V's in shape, and so the wood grain lines are pretty tight together, and they can look very different. Some of the blotchiness that you see on the right-hand picture are just how the stain is being accepted. And sometimes, especially, sometimes the trick to having a less blotchy stain, of course you can put more coats of stain and get it darker and get a more even soaking through. But some of the tricks sometimes you have to do to keep that blotchiness is to actually use a pre-stain in order to soak through so that the next real stain that you put on there will be more even in color and stuff. But anyways, so part of that is just the staining they're doing, and the staining helps you to see the wood grain better, so that's why I guess they're showing it this way. So seasoning. It's not Cajun seasoning. We're not trying to eat this thing, but they talk about seasoning of the lumber. So that's the idea that moisture content of growing wood can vary from 30% of the weight to 300% more than the oven dry weight of the wood. So by oven dry weight, if you take a block of wood and stick it in the oven and bake it for as much as you can stand, or for there's a correct amount of time, but I guess it just kind of depends. You can bake all the moisture out of this thing, and you've got a dry, oven dry sample. And that's what we compare to what we consider to be near 0% moisture in the lumber. And it'll be much lighter. It'll also be more rigid and stronger when it's dry. So after the lumber is sawn, it is generally seasoned either out in the air, naturally, or in an oven. Well, no, they call it a kiln, but it's the same idea. But of course, nobody's using their kitchen ovens to cook lumber. They do this in great big kilns that are large enough to run very long stacks of lumber through the kiln for a period of time from maybe 4 hours to maybe a day or two. It just depends. And it kind of depends what you need too. So seasoned lumber is lighter, like I said. It's stronger, it's stiffer than green lumber, and that's what we typically call the unseasoned lumber, is green lumber. But unseasoned is also correct. But more times in the industry, you're going to find people calling it green. Well, yeah, when you first cut it down, it's green, sort of, maybe. It depends. But we call it green nonetheless when it's heavy and full of moisture. So here's the thing. When you've got moisture in your lumber, funguses can grow in it. Termites can eat it up. They need moisture. The soft pallets of the teeth of the termites, they just can't chew that hard, dry lumber. They need some moisture. Now, some lumbers, like some termites, like the Formosan Formosan termite, called termites lumber and lumber termites. But anyways, Formosan termites bring their own water with them, so they can take a dry piece of wood. So you really have to be on guard for some termites more than others. But the basic thing we do to protect lumber is to make sure it's dry before we ever start framing. First of all, so you don't attract these critters, and you want to keep it dry after you've built it. So you don't want any moisture finding its way soaking into the wood. You need your wood to stay dry. That said, so what we normally try to do, our best practice in general, has always been, from the beginning of time, to keep the moisture content below 20%. And what that really means is 19% has been the standard forever. But in the last, I want to say, decade or so, which is still a long time, that standard has kind of moved down to 15%. Some of you may remember when we had the great flood in Baton Rouge area in 2016, August of 2016, flooded. A couple 100,000 houses got flooded. It was a big deal. So, yeah, you can't forget it. Well, as we were waiting, as we tore out the drywall and the insulation and all the contents of the house and get that to the curb, everybody was waiting and fighting with blowers and dryers and stuff to dry out their house enough to get the moisture content back down to 15%, because that's the magic number that we consider to be dried out enough to go and close it all up again. Because when you buy lumber at Home Depot, you buy any lumber yard, it's been kiln dried to 15% moisture content. And it could be drier than that. Oftentimes, if it's not been out in the moisture, even in the humidity of Louisiana, it will be lower than 15%, somewhat. And if that lumber was in Arizona or somewhere with a much lower humidity, then that moisture content will drop even more. But at the lumber mills in the kiln, their job is to get the moisture content down to 15%. But it used to be 19% that we would go to. Below 20%, which kind of means 19. So you'll see some things about that. So look at this picture. This one is particularly good for showing you how the lumber will shrink, how it changes shape depending on what part of the tree it was cut from. So you see that maybe the very best, least distorted lumber is the one at the very top here of this log, this completely considered quarter-sawn lumber. Now there's another one right below it that's also considered quarter-sawn, but it's running through the heart of the tree. And when that happens, it's denser material, so it'll tend to be a little chubbier after it's, gone from, if you cut it and then it shrinks, that's what the lumber yards do. They cut the lumber, they rough cut it, and then they kiln and dry it. And this is the kind of shape you can expect out of it. But then what they will typically do is then they will plane it or drum sand it to smooth it out, and they end up getting rid of some of the distortion out of that too. But you can see how extreme it is over on the right-hand side. That right-hand piece of lumber is perfect example of plain-sawn lumber, and you can see how it dried out, shrunk more along the outside of the log, and so it curved inward because of that. It changed shape because of that, and this is what something you can predict. So there's the things they can do to combat this. For instance, they can spray down the wood that's all got moisture in it with hygroscopic chemicals. You see the pair of red asterisks down at the very bottom. Sometimes the seasoning, they'll spray the wood with hygroscopic chemicals, which mechanically and even chemically combine with the water that's in the wood and kind of pulls it out and replaces it with the chemical temporarily. And then as they run through the kiln, they're baking all that out, but it tends to alleviate some of the shape change out of that, so it helps with that. Now, the shrinkage is more across the diameter of the log than anything else, but it also shrinks just about the same amount around the circumference of the log. The circle on the outside of the log is going to shrink more than the circles that are on the inside of the log, for a couple of reasons. Well, but basically it's because you've got more length, more dimensions to shrink. And so as you shrink the log, as you dry out the log, or as the log dries out, what you get up there, what you see at the very top, is it'll tend to crack open along there. When we're chopping wood, we look for those kind of cracks because we can aim for them with the axe, and it makes it easier to split the wood. But when you're trying to make lumber, you don't want those cracks. And so the hygroscopic chemicals help alleviate some of that and make the lumber crack less as it's shrinking. But ultimately, they try to cut the lumber while it's green still. It's easier to cut through a little bit. And but also to get it too close to its basic shape, and then strap it together as big bundles and dry it out in various ways, either slowly by air over time, which sometimes is useful, but more often it's running through a kiln where they're doing the drying. So they can dry it slowly and take 4 years to dry it out, or you can dry it in a matter of hours or maybe a day or two. Anyway, so that's that. The next thing is the seasoning. Okay, well, I talked about seasoning already, but here's another thing about the shrinkage that goes on with the seasoning. We have 3 terms for you to keep straight in your head. When the log does change length along the length of the log from here to way back to the other end of let's say a 20-foot long log, it'll change shape. It'll shrink some, up to 3% maybe. So that's a factor. But it's nowhere near the factor that radial and tangential shrinkage. So what the heck? We got 2 more terms. Longitudinal makes sense. You're talking about along the length of the log. So what is radial and tangential shrinkage? Okay, so radial shrinkage is talking about the radius of the log or the diameter of the log. And so generally that's around, it can be somewhere 5 to 10%. With softwood lumber, it tends to be about 10%. So that means what I just said earlier about the 10-inch diameter log, when it's moist, becomes a 9-inch diameter log after it has been fully seasoned, fully cured. So that's radial shrinkage. The radius, the diameter, if you think about those 2 things, that the diameter is across the whole width of that log. The radius is going from the center of the circle out. So diameter is twice the length of the radius in general. Okay, so that's radial shrinkage. So that's a factor. That's big. 10%. Oh my goodness. And then tangential shrinkage is where we're talking about the actual length of the circles of these rings. The outer band of pulpy material going all the way around this log is going to shrink a lot more than the inner one, because the inner one doesn't have as much wood to shrink, and so it can't shrink as much. And so, you say, oh, it's a percentage. Yeah, but it's not equal enough. And so that shrinkage tends to be around the same number, 5 to 10%. They're both the same issue, basically, or the same. They're two different ways of looking at the same problem here. Because it's changing shape, it'll tend to crack along there, and it's maybe the bigger deal, because you're more likely to have cracks in the lumber from tangential shrinkage, that distortion that's going on. But it's around the same 5 to 10%, where the softwood lumbers like pine tend to shrink about 10% tangentially. So we're talking about the circumference of this log changing, and it changes more along the outside circumference than it does in any of the inner circumferences when you're going around that log. Okay, so I'm not going to make any difference between radial and tangential, in that I'm not going to say that one is greater than the other. The author tries to say that this radial shrinkage is greater. I'm not so sure. I think they are both the same factor. They're the same thing, basically. They're all across the grain. Radial shrinkage or tangential shrinkage, you're still talking about shrinkage across the grain, across the log in some way, as opposed to along the length of the log. And the shape of the cells, the wood cells run lengthways. They're not perfect round cells, and they tend to run along the length of the log too, so that the cell shapes themselves give you something to go by on that. Okay, so yeah, the tangential and radial, there's a factor, but really on this graph kind of shows that tangential shrinkage is a bigger deal than radial. But the author of the book that I based this course on, he was going for radial. Yeah, I say they're both, at best, they're equal. And so I'm going to consider them both equal, and we're not going to worry about that. But they both, what's important for you to remember is that they are both a much bigger factor in shrinkage than the longitudinal shrinkage along the length. But that length is a big enough factor where I've gone and installed crown molding for stain grade crown molding, and have some real tight joints, and they open up, because up at the top of the ceiling it's pretty hot and dry up there compared to the rest of the house. So they can tend to open up joints that were nice and perfect. Makes you kind of angry, So yeah, there's some techniques I can talk about of how you combat that, but as a carpenter. But okay, so equilibrium moisture content is another thing. EMC, or equilibrium moisture content. Over time, I kind of alluded to it a little bit a few moments ago, where you get the lumber cured or seasoned down to 15% moisture content, but over time it'll dry out even more depending on the humidity that's in the air. So as you see in the Louisiana area here, how we're sitting there somewhere around 11 or 12. It depends, but 11 or 12% moisture content maybe. You can go and test that out if you got a moisture meter in your house, and you will find that there's two things going on. If you're talking about a shed outside, that's what they're really talking about. You can get the moisture content down even lower when you're talking about inside your house, where you've got conditioned air. You've got an air conditioner that is lowering the relative humidity in the house because it's taking moisture out of the air, a dehumidifier of sorts. But you can see over in the desert areas over on the west, there on the left side of this page, where they can get the equilibrium moisture content way, way down. So this is a problem. And then you see up in the northwest and the northeast and stuff, so the east will have more humidity, but you take a place like Montana and such, Kansas, they could be at 8%, but still the point is a lot lower than the 15%. So where this gets to be a problem is when you've got a fancy guitar like I do, and then I went from a very dry climate up in the northwestern part of Canada and drove here to Louisiana. I started having expansion problems, which caused some cracking of my fancy, very expensive guitar. So that's a problem where violins and cellos and other orchestra equipment, and it's a problem for pianos and all kinds of wooden instruments change shape with the humidity level. So anyway, so this is a term to think about here, is equilibrium moisture content is what you eventually get over time as that wood product dries out on your building. Some lumber stamping going on here. Let's look at this. When we talk about S4S, you see the first bullet. You see the lumber is surfaced to make it smooth and more dimensionally precise. Okay, that's a pretty good description. Framing lumber is usually surfaced on all four sides. So you take a 2x4. When you go measure your 2x4, you'll discover you got ripped off. It's not 2 inches by 4 inches. It's 1.5 inches by 3.5 inches. So it's a 1/2 inch less in both dimensions and such here. So, but it started off being rough cut, maybe pretty close to a 2 inch by 4 inch board, and then it shrunk through the seasoning process, and then they resurfaced it by, you say you run it through a planer, and that's certainly true, and that could happen. But most of the time for lumber, it's actually running through a series of drum sanders to get it to the right dimension. And then you get your true to pretty darn accurately at 1.5 inches by 3.5 dimension 2x4. So finished lumber could be surfaced on 4 sides or sometimes on 2 sides, and the other side you'll be sawing and servicing by the woodworker, him or herself. Now so when we say it's been surfaced by, sometimes you'll see a term S-dry, and that means it was surfaced after seasoning, which is the default. This is by far the most common way we do lumber. We rough cut it, then we let it dry out, which means seasoning it, and then we'll run it through some surfacing. So that would be S-dry, surfaced while dry, which also implies that you're at least dried it out to 19% moisture content. That was the standard. Surfacing before seasoning is maybe economical, might be good for certain species that don't distort much maybe, but generally they do. So there's less likely and less common to surface it while it's green. But if you saw S green, that tells you on the lumber stamp that it was surfaced while it was still green. And so you might be finding dimensionally unstable lumber that might need to be planed depending on what you need to use it for. Okay, so there's other things. We talk about the lumber grade. There's select, standard. There's number 1, number 2, number 3 grades. That's generally a structural grade. Looking at how many knot holes there are, but it's not supposed to be about the appearance. It's supposed to be about the strength of the board. Okay, so let me just kind of skip past that a little bit. The moisture content by default was 19%. MC from 19% moisture content. That's what surface dry means. So here's looking at some of that structural grading. So you got select structural, and then you got number 1 lumber, number 2, number 3, and then you can have something a little less than that. It was called kind of a construction standard or a standard or utility grade. The utility grade is going to be pretty lousy stuff, generally pretty kind of close to the kind of crappy stuff they might make a pallet out of, But then there's this special category at the bottom called stud. And a stud certainly has to have a certain strength level, which is generally number 2 lumber. But the stud means something else. It means that it has been cut after it was dry, cut precisely to a specified length. So if you have an 8-foot stud, then if it's truly an 8-foot stud, then it's 8 feet long. Exactly. And then when you go and frame it up into a wall with a bottom plate and a couple of top plates, then you end up with a wall that's taller than that. So they also make studs that are cut just right so that you will get an 8-foot wall in the end when you include the 1.5 inches on the bottom of the stud or the bottom plate, and then the 3 inches up at the top for the top 2 plates for the framing. And so stud means that it's been cut to a precise length. And so that's an important difference, and sometimes you don't want that, And so a lot of the studs are going to be shorter than 8 feet, or if it's for a 10 foot or a 12 foot wall, shorter than 10 feet, shorter than 12 feet, because of the 3 2x4 plates that'll be horizontal that stud will be nailed to. So that's structural grading. There's also an appearance grading that can come up. That doesn't come up for framing lumber, but it can come up for furniture building, for flooring, and such, where instead of using the numbers, number 1, 2, and 3, they use letters B, C, D, and such, and A and B, and it depends on, there's a little bit different systems on certain kinds of lumber. So cedar patterns, there was a lot, the lumber mills that specialize in one and the other, they tended to evolve a little differently on their grading parts over the years. So wood has both tensile strength, where it can be pulled and stretched like a cable, and compressive strength, where you can squish it. Concrete only has compressive strength. Steel has compressive and tensive strength, and wood has both compressive and tensive strength. Anyway, so the strength varies significantly with the direction of the grain, a lot. So along the length of the log, you've got great tensile strength and compressive strength. And it depends on the species of the wood, and it depends on the presence of how many knots there are. And remember that when you see a knot in a tree, that's the place where there's a branch that was sticking out of that tree, that grew out of that tree. And so with pine trees, as they get taller and taller, they tend to lose the branches that are lower down. And so some of the branches that were a factor will be deeper into the tree. And then as you get a tree that's been around for a long time, you can have no knots down for long periods of long stretches of that lumber because of the branches that have been lost over time, So defect-free wood is close to the strength of steel if you rate it on a per weight basis. For pound, the steel is just as strong as steel. But the typical grades are weaker. But if you got defect-free lumber, it's surprisingly strong. Strength can also vary by the duration of the load. Okay, so you can put a load on it for a short while, and that's a different thing from having a load for year after year, where it can slowly change shape, the lumber, And then, of course, if there's high humidity, that changes how much load that wood can take, because it's going to be moisture, which means it's going to be more flexible, which is not always a good thing. You don't want your beam to be sagging, And if you put certain chemical treatments, that affects it too. That can tend to make it softer. And so pressure treating is a problem. It's a good thing when you're trying to fight the bugs, but so generally, if you have to make a pressure-treated piece of lumber structural, where it's going to be supporting, like a beam, supporting a load of some kind, you need that lumber to have been either re-seasoned, where it's run through a kiln, or it's been dried out over time, or one way or the other. You don't want moist wood being used, even when it has a pressure treatment, because, the bugs won't eat it, but it can still change shape and be a saggy old beam in the end, Okay, so this is just kind of illustrating the tensile strength of steel compared to wood, but if you go by its pounds, it actually can be equal to the steel for its weight. Okay. Now we're getting to lumber dimensions, and this is an area, the only math we have in here is where you're figuring out some board feet calculations. So I'll get to this now a little bit, and I'm going to do a little explanation here, but I'm going to then make a separate video to deal with the math for exam 1. So when you're looking at the actual sizes of lumber, and then you can compare that to the nominal size, so the 2x4, the nominal size of a 2x4 would be 2 inches by 4 inches. But when you actually measure the 2x4, as you see on the second sub-bullet on this page, 2x4 actual dimension is 1.5 inches by 3.5 inches. And I just said that a couple of times a few moments ago. Now, if you look at 1x4, well, the 4 inches stays the same. It's going to be 3.5 inches. But the 1 inch dimension, instead of 2 inches for a 1x4 compared to a 2x4, is 3/4 of an inch. So you subtract off a 1/4 inch for 1 inch. From 2 inch up to 6 inch, you subtract off 1/2 inch from the dimension. So, 1x4 is 3/4 by 3.5. A 2x4 1.5 inches. So it's double the thickness, and it truly is. But once you get beyond the 2x6, okay, a 2x6 would be 1.5 inches by 5.5 inches. So that's true. But once you get beyond 2x6s, 2x8s, 2x10s, 2x12s, then the 2-inch still stays the same. It's going to be 1.5 inches. But the 8-inch board, the 10-inch board, the 12-inch board, they officially subtract off a 3/4 of an inch. And so a 2x8 is considered to be 7.25 inches wide, not 8 inches. So it's 3/4 less. The 2x10 is considered to be 2x10. I said it is supposed to be basically, in theory, 9.25. Sorry, I'm just need more coffee here, I guess. And then a 2x12 be 11.25. So you're subtracting off 3/4 of an inch for each of these numbers. But in reality is that they don't worry about making those boards exactly that number when they're planing them out. And so you can't completely go by that. It's true in theory, but in reality, if you take a long enough 2x12, you measure at one end, you might measure 11 inches instead of 11.25. And at the other end, you might be reaching closer to 11 7/8 or almost 12 inches at the other end. They can vary that much across from one end to the other end of the board. So they vary. It's not as precise, but for 1x4, 2x4, 2x6, it's very precise, which makes some great lumber to be framing up a house with. Lumber where its smallest dimension is greater than 5.5 inches, where it's smallest of the two. If a 2x4, the 2 is the smallest dimension of a 2x4. So with some kind of big old lumber that's where the smallest dimension is 5.5 inches or greater than 5.5 inches, then we would call it timber or heavy timber. Now, in some versions of that, people will say if it's 5.5 inches or greater, then it's heavy timber. So I'm not going to sweat the small stuff. Greater than and or equal to 5.5 inches for its least dimension, its smallest dimension, we call it heavy timber. We'll stick with that. But so there's some disagreement in the industry on whether you call it heavy timber when it's equal to 5.5 inches. But if it's more than that, it's always considered heavy timber. So that's an important thing that'll come up because our very next chapter will be about heavy timber, which won't be on our first exam, but it will be on the next exam. So, but you do need to know this factoid for this test even. Last bullet on the page, it says, in US, the lumber is priced by the board foot, based on a nominal dimension, not the actual dimension. So even though you need to know for framing purposes and for lots of other reasons, you need to be able to know what the actual size of these boards are, that's important. But when we're calculating board feet, they round everything up. So the 2x4 is just going to be simply a 2x4. We're just going to be using those numbers. A 2x12, yeah, it's 1.5 inches by 11.25, but no, for board feet calculations, it's a 2x12. That's all you do is we use that rounded up nominal number. Now, in a very perfect, simple way of describing what a board foot of material is, if you had a 1 foot by 1 foot board that was 1 inch thick, a 12-inch by 12-inch board that is 1 inch thick, then we consider that a board foot. So generally, up to 1 inch of thickness, everything gets rounded up to the whole number. So up to 1 inch thickness, any board, every square foot for hardwood flooring, every square foot of wood that you put on the floor would be considered a board foot. But if your hardwood floor is more than 1 inch, it gets rounded up to the 2-inch number. And so then every square foot on your floor of hardwood flooring will be 2 square feet. Every square foot will be 2 board feet, sorry. So yeah, if your board is 1 inch or less, then every square foot is 1 board foot. That's the simplest way to describe it. So I want to flip over to a table. So I've got a table here, and actually there's continues in this. There's two tables. And the first three columns are a table dealing with 1x material. So, remember the 1x material, the 1 inch number is the nominal number. Well, it's actually 3/4. So a 3/4 material all the way down the column. On the second column, you see the actual size. Well, 1x2 is really 3/4 by 1.5. 1x4, 3/4 by 3.5, and the 1x6, 3/4 by 5.5. And then they start subtracting off the 7-inch and then, the 11, the 8 and the 10 and the 12-inch numbers. They subtract off 3/4 of an inch. So then you get 3/4 by 7.25, 3/4 by 9.25, 3/4 by 11.25. Okay. So, meanwhile, over on the other column, those dimensions, the nominal column on the, if you go more than halfway across the page, I got a second nominal column dealing with 2x4s, 2x6s, 2x4, or whatever, 2x6s, 2x8s, 2x10s, 2x12s. Okay. Anyways, let me take a sip of coffee. It might help. So yeah, the dimensions are worth looking at this table. It can help you see the patterns. But you see how I've got two places where I've got a group of 3 columns in red, because a 2x6 is actually 1 board foot for every foot of it you have. So if you've got a 10-foot long piece of 2x6, you've got 10 board feet. If you've got a 20-foot long 2x6, you got 20 board foot. So every foot of it is equal to 1 board foot. And look over on the left column, the first column down at the very bottom, 1x12. Well, think about it. If it's a 1x12, it's 12 inches wide, or 11.25-ish. We round it up anyways to 12 inches. And so for every foot of that stuff, it's only 3/4 inch, so we're going to round that up to 1 inch. So for every foot of 2x12, you get 1 board foot. So a 1x12 and a 2x6 have the same properties in that every foot of it is equal to a board foot. So that's kind of handy to know. It could be useful if you're dealing with those particular ones. But so the actual calculation that we do, we talk about linear measure, when we're talking about this, when we're trying to deal with the board foot and the surface area and everything. So why do we care about this? You go to Home Depot and you can buy, and Lowe's, you can buy lots of lumber where you're never going to have to calculate a board foot. But if you're buying lumber for Home Depot, you will be. And if you wanted to go in and find out what the lumber costs are, you can go get a few sample board prices for the lumber, and then you've got all you need to calculate all the other board foot prices. So it can be handy. If you're a big company that's doing fencing, you're buying lumber by the train car, you're buying it by the board foot. And, if you are buying hardwood lumber for flooring, for furniture, anything, all hardwood lumber is sold by the board foot. That's how they calculate it. And just like the casinos, house always wins. They round up. They never round down. They always round up. So you end up buying less lumber than you might think you're buying because of that. Okay, on that depressing note, let's go to the next page where we're maybe ready for a break. Well, I'm not gonna dwell on this math much longer, and so it'll be I'll wait and make most of this math effort into a separate video. So back to the wood. I thought I had I cut out the word problem in here, so I'll be dealing with that. That's what I did. So in here, I've gotten rid of the word problem that I was going to work on. I'll show you how this works, but we'll come back to this table later. But you get the concept down. Every single square foot of the lumber is if it's only 1 inch thick or less, is a board foot. If it's somewhere between 1 inch and 2 inches, well, then every square foot of your flooring will be 2 square feet. Okay, 2 board feet, sorry. Okay, so let's look at lumber a little bit more. We're going to finish up this chapter in a little bit here, but let's look at some of these wood products here. We've still got a ways to go. We're about more than halfway, though. Okay, so here we're looking at wood I-joists. This is engineered lumber. The trees don't grow like this. You know, they're putting together and making a wood product that is a beam, an I-beam, in fact. And what these things are used as replacements, typically for 2x12s, for floor framing and sometimes roof framing. They're very light and nice and rigid. They burn like crazy, though. They burn faster than normal lumber, so that's their big kryptonite, their big weakness. But in wood I-joists, that's a type of engineered lumber. So that's what we're going to start looking at, is some of the lumber products here. So solid wood and wood fiber materials can be used in the manufacture of various wood products. Because of the loss, we've over-forested so many, or over-harvested so much lumber that there's just no large trees left to use, even if we were to take our time on, because we just irresponsibly messed up a whole bunch of forests across the country. There's very few giant logs. I've got some pictures of logs that you'll never see on the road, hardly ever. You know, from years gone by, but they're all gone pretty much, except for a few protected forests they're kind of part of a state park system or something. Anyways, with manufactured lumber, you can get a product with fewer defects than you would, because you could literally take a tree and kind of make your wood product out of pieces of wood instead. So it's a more efficient use of the wood materials. In some cases, you're making a stronger, stiffer piece of wood than you would get with the original solid wood. Generally, they're a little heavier most of the time. The I-joists that I was talking about a moment ago is maybe the exception. But a lot of the stuff, when they put a bunch of glue together, it tends to make it heavier. Okay, so the original engineered lumber was the glue-lam beam. Glue-lam, or the glue-laminated beam. It's made up of a whole bunch of, let's say, 2x4s or other blocks of wood of that sort that are all glued together. And instead of worrying about whether you got long enough wood to have continuous wood through there, typically they can join this wood. So in this picture, the second row from the bottom of that beam at the top, the page here, you can see what we call a finger joint, where they've routed on each end of each board these fingers that will fit together to make a lot of surface area to glue. And so that's one way to get a good joint. Now down at the bottom in those little blue drawings are showing you the finger jointing, that how that's done to join wood in molding and in beams like this. That doesn't look particularly good if you're doing stain crayed wood, so it's not used for that. It's used for things that either don't matter because they're not going to be even seen. Like that glue-lam beam won't be a feature most of the time. In this case, it'll be hidden in the wall, you know. But if it's part of molding, if it's part of something that's going to be seen as a feature, then they wouldn't want that. So sometimes a simpler joint would be a scarf joint, where they do a long slope angle that you see in item A of the three. We got A, B, C of those little blue figures. Well, item A is what we call a scarf joint, and so is that thing with the baseboard we're looking at. When you cut an angle like this, you get a more length to glue the surfaces together to make them act like one. And it also tends to make the joint disappear now, so it's not seen as easily, especially if you're looking from the left at this picture as opposed to looking from the right, and it'll tend to hide it better. Anyway, so scarf joints and finger joints are used in joining glue-lam beam lumber pieces and other joinery of pieces along the ends for the butt joints. A butt joint is where you just have two 90-degree cuts and you butt it. Well, you're not going to have enough surface area for the glue to be able to help to join those together. So the scarf joint helps. So now I've got several different types of engineered lumber to talk about here. The laminated strand lumber is the one at the top left, and it just looks like OSB, oriented strand board, the wood chip material. So it's the least strong product mentioned on this So it can be used for short spans, maybe over top of a simple doorway, as the header beam to span across and transfer the loads. But the other two are pretty much equivalent, and they are wonderful for use as beams for spanning great distances, carrying heavy loads. So the one at the bottom is the second bullet on this page, laminated veneer lumber, LVL. So that stuff is kind of looks like plywood. And if you look at it just the right way, you say, oh, that's a bunch of plywood stacked together. No, it's actually one solid piece of wood, engineered material, where the veneers have been glued together just like they do with plywood, except that with plywood, every other layer is rotated 90 degrees so that you get more strength and you don't have splitting. Here, for strength for carrying loads as a beam, all the wood grain levels are running the same direction from end to end along the long length here. So that's LVL, or laminated veneer lumber. And then the last one is that drawing is representing it up at the top right-hand corner, in the corner of the page there. You've got what looks like a whole bunch of twigs that are all kind of stacked together and glued together, and that's really what it is. Parallel strand lumber. The strands are little twigs that they have stripped out of young trees, so they don't need an old growth tree to make a great big huge girder. They just shred up a tree into twigs and they glue it together, and that's probably the most efficient use of lumber for heavy beams, heavy timber beams and such. So that's probably the most enduring, the one that'll win the race. You know, for years and years, LVL and PSL, laminated veneer lumber, and this twig-based thing called parallel strand lumber, or PSL. Normally the LVL and PSL have been competing with each other, and they still kind of do, but I think parallel strand lumber will win the day on that, as far as and it's already starting to. The economics are in its favor. But I tell you, it's some heavy lumber, because there's a lot of glue needed to glue all those twigs together, and glue is heavier than wood. Okay, so we call that engineered lumber, but up at the top you see the title says structural composite lumber. Ooh. So yes, that's another technical name for it. On my test questions, I would list both names, and most of us will more easily remember, I think, engineered lumber. Most of the industry actually calls it that. It's only in textbooks that you see it. But so you'll see both of them listed together in the test questions in this course. So structural composite lumber is another name for engineered lumber. Then there's wood combinations with plastics that are used to sometimes for some siding, sometimes for some decking boards. So actually probably the most common place you're going to find that used around here that doesn't work very well in the intense sun we have here for a siding, but it does work pretty good for a decking material. So you'll find kind of a plasticky material that actually has some wood fiber in it. So they're taking the sawdust, and we're taking recycled plastics and making a decking board. And so it's a pretty good idea. But that stuff does expand and contract quite a bit. And so decking it works pretty good for compared to siding, because you can have gaps in the decking to allow it to expand and contract and to keep it from buckling. Structural wood panels. We're starting to move into plywood. And one of the plywood substitutes out there that's very, very successful has been basically a kind of particle board, but we don't call it that. It's called oriented strand board. So the third bullet down on this page says oriented strand board, or OSB, the abbreviations for that. So the original panels, 4x8 sheets, would be plywood, where we have laminated veneers, every other layer rotated 90 degrees from the other one. So there's always, the front and the back are always running the length of the 4x8 sheet, you know, top and bottom in this picture. So that means that you've always got an odd number of veneer layers. You're not going to have an even number layer, because the front and the back are running the same direction. You either are going to have 3 layers, 5 layers, 7 layers, 9 layers, 11, or it could be 31 layers or whatever, but it's going to be a whole bunch of layers together. And it, by its very nature, keeps it from splitting because you got veneer grains moving both ways across there. So structural wood panels is a generic term, fancy name for plywood, except that it does include things that are not made of layers or veneers. So when you start looking at OSB, it's a bunch of wafer chips, a whole bunch of wood chips that have been purposely randomly laid down in beds of glue and layer upon layer. And out of that, you end up, you get the oriented strand board, but it's something that it's a very efficient use of wood products. So again, you don't need big trees to make this stuff, whereas with plywood, you do need decent quality trees so that you can peel the log of the veneer. So I'll have to show you how that works. Particle board, again, a very efficient use of wood because they're taking sawdust that we've got is always so plentiful and turning that into a solid piece of particle board that's quite dense and heavy. Again, because that glue is heavy. Then there's another board called fiberboard, where you've got fine-grade wood particles, much finer than even sawdust, that are all glued together with the glue, and it tends to be mostly in quarter-inch thicknesses, maybe 1/8-inch thicknesses, and that sort of thing, as subfloors over top of other subfloors. But anyways, the wood grain of laminated veneer is distorted and is not as pleasing as solid wood for furniture and trim. And so a lot of this stuff does not do well when it comes to making furniture, but the vast majority of our lumber that is harvested across the world is used for framing up of houses. So that's not an issue. Anyway, so when we say structural wood panels, we're not just talking about plywood. It includes all plywood, but it also includes things like particle board, which are and oriented strand board and fiber board and stuff that are not really truly plywood products. The standard size for plywood normally would be 4x8 sheets, but you can get it special ordered in bigger sheets from the factory. The thicknesses kind of run from maybe 1/4 inch or 5/16 up to about 1.125 and even I've seen even thicker than that. So plywood, on a plywood lumber stamp, they'll have a span rating like 32/16, which is used as roof sheathing spaced at 32 inches or as subflooring over joists to walk on, where people are going to be walking on, where it needs to be joints at least 16 inches apart. The actual joints of the floor framing, so that you can stand on it and without it deflecting. So the other thing I need to bring up is durability. So let me get a swig of coffee again. I'm getting a little woozy, sleepy. And you might be too. But anyways, let's see. With you, you can stop the recording, but me, I kind of need to keep going. The quality of and the type of glue that is used to glue these structural wood panels together, whether it's going to be wafer chips on an OSB or veneers of some plywood, they have to glue all these members together. So there's an exposure rating. I'll get it here. Exposure rating of exterior. So exterior glue is going to be the best for exterior use. For permanent exterior sidings will be used. There's an exposure 1 and an exposure 2 level. And so exposure 1 is better than exposure 2 as far as moisture. So exposure 1 can be used on exterior use. Exterior glue, medium quality veneers. For interior use with prolonged exposure during construction. So that's maybe the most common example. And then exposure 2 is for interior use only, and so then you need to make sure that you've gotten that material indoors, because it's never supposed to be out. So what you find is that if you're going to go to the store and buy some oak plywood or some birch plywood, it's not used for framing or houses or for roof decks and sheathing on the as outside of the walls of a building. No, it's used for furniture or used for closet shelves maybe at at some level, but a lot of times it's for some kind of furniture use, cabinet that you're building or something, shelving unit, something. And it's not going to deal with moisture, so that kind of material, that kind of lumber is very vulnerable to high humidity. So having it outside in Louisiana is a bad thing. It'll tend to separate over time. And by the way, the glue, the bugs tend to like it better anyways because it's animal-based, whereas the exposure one and the exterior glue rating up top here, those are both using glues that are not made from animal parts in any way, shape, or form. They'll use a urea formaldehyde-based glue sort of thing. Okay, so the adhesive that is used to make the exterior glue, this is the takeaway from this page, the most important thing, this last bullet, it says, the adhesive used to make exterior grade plywood is more moisture resistant than that used to make interior grade plywood. So it's something that's kind of obvious as we talked about it, but it's a factoid that could be turned into a test question. So you just want to make sure you understand that. Now, making of plywood, well, they'll take logs and they'll literally have a knife edge on the end, and as they kind of peel the log like a roll of toilet paper. But they've got to do it with some very elaborate chisels that are pushing and vibrating and to peel the wood away from the log itself. And that's how most veneers are made. And then they can glue them all together as pieces. So yeah, kind of like unrolling toilet paper. But of course, what they really do is have a knife edge and they're torquing that load of the log around the corner. So here's some veneers patterns. So the top veneer pattern is what we were just talking about, the rotary slicing, where you kind of rotate the log and peel the outside, and you're basically taking one of those growth rings off usually. But there is such a thing as plain slicing and even slicing, and there's also quarter slicing where they can slice off pieces. But the vast majority of veneers you're going to run across are going to be done this way with the rotary slicing. So they literally stick and point the actual blade in just the right angle, and they keep working until they start getting it to peel, and usually the thing will move pretty quickly after that. So there's the same picture we were looking at. Oh, I know, I'm hitting the wrong way. That's why. So yeah, this is what I was looking for. It's showing you kind of a diagram here with how they do this. Most veneer by the rotary knife. Here they're running a bunch of fur into veneer for some kind of plywood. This is a smaller little outfit. You're talking about the typical plywood plant. Nowadays they're huge and automated, unlike this. So again, even number, you're going to have an odd number of plywood veneers almost in every case. A little factoid that could be turned into a test question. So we have different grades of the veneers, different qualities. As you can imagine, if you got knot holes and cracks when you start peeling that log for the veneer, you'll get different grades of veneer. So we have a system from A to D, where A is the best veneer and D is the worst. So we got A, B, C, and D for veneers. And so when you've got BC plywood, well, then that's got a B level on one side and C throughout the rest of it. If you got an AC plywood, you got even better quality on there, and that changes the formula for what's due when and all that. Let's see. So A through D, where A is the best veneer and D is the worst. There is one more that doesn't show up on this list. It does show up in the study guide. I don't know, maybe it is somewhere on this page or some other page, but I've tried to get it in there a couple times and I see it's not there. And that is, if there's one grade better than A, and it's N, the letter N, like nope or like new, so yeah, N is better than A, which is better than B, which is better than C, which is better than D. So CDX plywood is a lower grade, and you can see the C and the D that are showing up there. Oops, lost my page here. Okay, so let me skip along here. Wood treatments. So there's fire retardant treatment you can get. There's a chemical salt that is pressure treated into the wood under pressure. Pressure impregnated, they're calling it here, but it's under pressure that it's pushed into the wood surface by under high pressure, usually in a vessel. So again, there are some places where you can get away with a little bit of wood in a commercial code if it's treated for fire retardancy to keep it from burning. And so typically it'll be some kind of a salt. Whereas preservative treated wood, that's the stuff to preserve against bugs, from insect attacks. And so that's a different kind of pressure treated treatment, which is the one we're most familiar with day in, day out. It comes from, anyways, the whole thing here is with insects. They'll eat this stuff, and the pressure treated lumber, the preservative treatments we put in there, which are normally what we call waterborne salts of various kinds, they keep the bugs at bay. So wood that is exposed to the weather, in contact with the ground, or in areas of high termite risk, you have to pressure treat. So we typically, the only pressure treated lumber you're supposed to have on a typical house is the bottom plate. You can do the bottom plate because there will be some shrinkage level that's going to happen there that can start tearing apart a house. If you were framing a house with pressure treated lumber, you're in for trouble. So I've got a whole page here showing you of various kinds of treatments. So the original treatment was the top one, creosote. And that's an oily derivative of coal. And you get it on your hands and rub it on your body. Anywhere you touch when you got this stuff on your hands or on your gloves, you wipe your face or wipe your nose, or you get this black stuff on your face, and you'll have a chemical burn that'll be glowing that night. You'll be miserable. You won't get any sleep, probably. But that's not a waterborne salt. But pretty much everything else on this page is. So the arsenic, copper, and boron are the chemicals we have actively used as pressure treatments. So the copper has amazing preservative properties, so it works very well, but copper is expensive. Arsenic is cheaper. So the original pressure treated lumber had a lot of arsenic and some copper in it. And then eventually we started seeing that the pressure treated lumber was getting much greener because they started reducing the amount of arsenic in it because it's so poisonous to us, and putting more copper in it, but that drove the price up. And then a lot of the modern pressure treated lumber has boron in it, the boric acid as a solution pressure treated into it, and it's not as effective as copper or arsenic, but you'll see it. That's the yellow wood. I think they have some other magical things in there now than what they used to have that may help too. But so that's probably all I should say about that. That's enough, because there's plenty of stuff on here, but I'm not going to ask test questions on it, and I need to, in the interest of time, keep going. The wood fasteners. Oh yes, that was the other area I was trying to remember this coming. So when we talk about fastening the various wood parts together or to other things, we got to know about the nails and the screws and the bolts and the split rings and all the various brackets that we use. And so nails are relatively inexpensive fasteners compared to other fasteners. They rate them by by length and the diameter of the shaft with a traditional nail. So a traditional nail that you actually hammer in with your hand, a 16 penny nail, 16D nail, would be it's going to be a little longer and a little bit bigger diameter than a 12 penny nail. So a 12 penny nail is 3 1/4 inches long. A 16 penny nail is 3 1/2 inches long. But the shaft is a little less. But if you get the framing nailer where you're automating this by shooting nails in with a nail gun for framing, the 16D nail and the 12D nail and the 10D nail and maybe the 8D nail that you can shoot out of that gun, typically, they're all going to have the same diameter shaft. So the nail gun kind of changes that. But you could actually see that the 16D nail was much stronger because it was huskier, heavier. And there's no really good formula for remembering these different lengths. A 2D nail is 1 inch. A 6D nail is 6 inches. So it's helpful to memorize a few of them so you know some of them for your career. But in here, not so much. I mean, I just want you to understand that, yeah, the higher the number, 16D is certainly a longer and a heavier nail generally than a 10D nail, which is 3 inches long, and that kind of thing. So 16, larger the number. Now that D, we say 16 penny nail, and why do we have the D? Because it used to be a 16 denarii nail, and now we've decided to convert to a different currency, but we still have the D, but the D came from denarii. Okay, so with that, there's different finishes. You can have bright plain steel that rust more easily. You can have galvanized coatings on the nails, which is a galvanized coating has zinc oxide coating on the nail, either galvanized or hot dip galvanized, or sometimes a combination of the two with some of the very best nails. And then you could even get stainless steel nails. Those are not going to be cheap. There's aluminum nails and copper nails, but those are mostly just very specialty things. And you got the different shapes of different types of nails. The common nail is most commonly used for framing. A box nail is more slender than a common nail. A casing nail is like a big finish nail, but it's meant for exterior finishing, compared to a finish nail or a brad nail that are meant for indoors, generally. The deformed shank, either a spiral bound or ring shank like this, as you see down underneath brad nails, is something that's great for something like fencing or subfloor to put down, because the ring shank is really hard to pull out. When you shoot it in with a nail or you drive that thing in one way, it doesn't like to come out. It'll tend to come out in pieces, so it's got a lot of holding power. They also sell a coated sinker, and the coated sinker has a sticky substance on it that will stick to the wood. As you drive it in, it's fine, and then when it comes to pulling it out, it's kind of gotten stuck there. So you tend to end up with those kinds of nails from the ring shank or the coated sinker. You tend to pull off the head and you don't get the rest of the nail. They also make a special high carbon nail for hammering into concrete or masonry. There's this old-fashioned nail that's made out of sheet metal called a cut nail. That you can actually buy those things if you need to have a certain special effect, but you wouldn't normally use them otherwise. And then just another example, there's so many kinds of nails out there, but the roofing nail is going to have a very big head, and so did the drywall nail, gypsum nail, except that hardly anybody uses them anymore because screw guns made it much better to use the screws for that sort of thing, but I've still got some. I'm sure they still exist. They're not a collector's item. But anyway, so they're just some of the shapes and their purposes. The brad nail is usually for something really thin as far as molding, like putting shoe molding onto baseboard, because it's a very tiny nail that you can shoot in and not leave a big old ugly mark to have to cover up. Finish nail is used for a lot of trim in a house, casing and such. Okay, now moving on to screws. Now, if you've got a screw and a nail of the same size, one's equivalent to the other in size and shape and diameter, the screw will have 3 to 4 times the holding power. So I know for a fact that a 16 penny nail, 3.5 inch long nail, a 16 penny nail has the holding power of about 100 pounds that you can pull straight out in softwood lumber. It's good for at least that amount. Whereas a number 9 3.5 inch decking screw, similar sizing, it takes up to 400 pounds to pull that thing out. Just grabbing a hold of the head and prying it out with a crowbar. So the screw has much more holding power. And then the bigger the screw and the more aggressive the screw pattern, the more holding power they can devise in there. So you get lag screws. They are big, heavy shaft things. You always have to pre-drill for them. They will, if you didn't, you split the wood, is why I'm saying that. You could find a way to screw it in there, but it could split the wood and start damaging whatever you're trying to save. Yeah, but they can have tremendous holding power because they're so big. So again, this size matters here. Now, when you look over on the right-hand side of this page, we're looking at bolts. A couple of different kinds. A machine bolt that's got a hex head on, and then hex shape for the nut. Then you got a washer on here. So generally, washers help to distribute the load in the wood because, you can start tightening if you drill a hole through two pieces of wood and bolt it together, where you could sink the hex head into the lumber where you can't even grab it anymore, And so the washer helps to distribute the load more and allow you to have even more holding power to bolt something together tightly. The carriage bolt, it's going to kind of sink in on purpose and leave the head so that you can't grab a hold of it, but it's likely to be held by the wood as it squishes inside, So washers are an important thing, and make sure you have the right size and thickness of washer for what you're trying to do. But they give you tremendous fastening ability here. So screws, and now bolts even more than screws. It's because the bolts are compressing two pieces together, particularly if you can get a good, strong, heavy washer on each end before you bolt it together. So then there's plates that can be used for fastening. The traditional joist hanger is something that maybe many of you have seen for attaching joists, for floor joists or ceiling joists. And they're an important item. There's hurricane straps that are used to hold rafters down, and so we use a lot of metal fasteners. There's special brackets meant for posts to keep the wood off the ground and anchor it to get a good connection between the concrete and the post. You do that with with metal very often. There's mend plates that can be driven in for joining two pieces. And then the one I wanted to show you in detail is the one at the very right-hand side of this page, where you've got a bolt and a nut and bolt affair that you're bolting two pieces of wood together. But besides that, they've augured out on one board and on the other side of the other board a cavity for a split ring. That's a spring steel piece of steel that is just the right size for this auger that you augured out so that you can slip that in there between the two pieces. And that makes, and it's kind of springy, so when you fit it in there, it's going to be tight in both. And so it's half in one board and half in the other. So when you then run that bolt through with a big heavy washer on each side, you can make an incredibly strong connection between two pieces of wood. This is a technique that's used a lot. It has been used a lot for 100 years and more in building train bridges, train trestles. You look at some of these old heavy timber train trestles that are for bridges for trains. Trains weigh a lot more than 18-wheelers. A locomotive itself can weigh 250,000 pounds and more. The locomotives have to have a lot of weight in order to have the traction they need to pull all those train cars behind them without just spinning the wheels on the steel train track. So yeah, it's a special kind of connection. And what's nice about it is you really only see the bolt, and it seems so innocent. Oh, it's just a bolt. It's fine. And there's a whole bunch more going on inside between those two pieces of wood. In the train business, they'll use a special kind of nut and bolt affair with a great big cast iron washer, so that you've got a lot of strength there with that to tighten up until you're just sinking it out of sight. Okay. So, coming near the end finally here, fastening corrosion or dealing with corrosion resistance. You need fasteners that won't rust away if they're going to be for exterior applications. So stainless steel can be used, copper can work, special paint-coated fasteners sometimes used. So we have most of our decking screws now for exterior decks are going to be painted screws with a very special high-grade paint. They can take a lot of beating and last a long time. And then the screw is a high carbon steel. We've got a lot of carbon in them, which they don't rust as easily either with the carbon. Hot dipped galvanized would be superior coating to an electroplated galvanized protection. So there are some nails that you can buy that are hot dipped, and they'll have a much thicker galvanized coating compared to the other nails that you can buy that are electroplated. But the electroplated are going to be skinnier and slimmer and maybe easier to work with. And then, so it depends on how long you need this thing you're building to last. And if galvanizing isn't good enough, because it's basically a coating on a steel nail, and so the nail that's underneath is still going to rust once that coating fails. Now, aluminum fasteners, they do exist for certain things, but you should never let aluminum fasteners touch for long term any concrete or masonry mortar. Anything based with Portland cement, like concrete or mortar or masonry block, the aluminum reacts violently with them over time. In fact, aluminum powder is an additive. We will grind in very, very fine powder and add to concrete in very small amounts in order to combat the shrinkage of concrete by adding a little bit to combat it so that it expands at the same rate it's shrinking. But the point is, aluminum, you never want to use aluminum fasteners. And most common place that we run into this is when you take flashing around a chimney and embed it. You know, if you use aluminum flashing, it won't rust, but it will react with that mortar that you're embedding it into. Okay. Most lumber pressure treatments cause corrosion too, because they are salt-based, and so you can't just use good old-fashioned steel nails in pressure-treated lumber. You need at least galvanized coated nails, or better, or more likely a coated screw. Manufactured products, there's other products here that I hadn't mentioned, so there's just a brief mention here about trusses. So when you look at this roof, a traditional rafter roof where you've got cut two rafter boards to go and lean them up against a ridge board, you get a very different look here. When you look at this picture here, there's no ridge board. So when you have a roof with trusses, that's the first thing that's a giveaway that these are truly trusses, because there is no ridge board. Whereas when you have rafters, you've always got to have them lean up and mashed and sandwiched together on a ridge board at the peak of the roof. So with trusses, when you get into areas of the country where they have serious and predictable snow loads, they can't build the roofs the way we do here. And commercial roofs here are still built with trusses because of the liability issue in the building codes and stuff for commercial buildings. But for houses here, you don't need to engineer your roof. You just got to follow the instructions of the building inspector, and he's got to agree that your roof is strong and all that. But there's no engineer to pay, typically. But in an area that has any significant snow loads over a 100-year period, so some areas that don't get snow too often still have to follow this, that you have your roof engineered, which means typically you're going to do that with trusses, most likely, because otherwise you got to bring it in. The building inspector won't sign off on it in those areas, so you'd have to have an engineer sign off on the roof one way or the other. And it's more affordable when you buy trusses because they come with the engineering built in. As long as you were installing it per the manufacturer's instructions, the engineering came with the trusses. So a lot of the trusses are made with 2x4s and 2x6s, and they're quite lightweight and they're quite flimsy and such. So that's one thing. And then I mentioned that at the very beginning we were looking at I-joists, wood I-joists. So Weyerhaeuser has the TGI truss joists. But they span further than solid wood. They use a lot less raw material, and they're lightweight and pretty rigid. They need to be braced well, but they're strong if you can keep them well braced. They got a top and a bottom flange. In this particular case, it's made of the LVL, the laminated veneer lumber, for the top and bottom, and then the middle part is OSB. So you got less trouble with crooks and bows and twists. Not as fire resistant though as conventional lumber. So the comparable lumber, if you had a 2x12 and that was what this dimension would be, those 2x12s will last a lot longer in a fire than these boards. So that's the kryptonite, and you need to remember that's the testable point that can show up here that I want you to know, is that these wood I-joists, they're not very fire resistant. They are the worst, really, of all the wood products. So the web of this I-beam is OSB. So these things are sold commonly in 20 and 40 foot lengths, and you can special order them up to 60 feet long. And they're all going to be nice and straight when they show up. So just skipping along, here's some factory built housing of sorts of some kind. So modular construction certainly is becoming more and more advanced compared to the mobile homes of years gone by. And so that's going to be more of a thing as time goes on too. But, I'm not going to address it too much. So at the end of this chapter, just like at the end of chapter 2, I have a bunch of links here, 5 pages of them, including the author's blog, Iano Backfill. Then these are to help you to kind of flip through some of these websites to see about possibly choosing your topic. You've got an essay to write for this course, a 1,200-word essay. It's about 4 pages double-spaced. That's going to be due to near the end of this semester. So you want to start thinking about that now, because in another few weeks you'll have a outline for your essay to submit. So you got to start thinking about it and planning for it, so that you can. I'm not after a complicated outline, just kind of a 1-page thing. Okay, so here's the Iano's Backfill. There's the Forest Stewardship Council for the green, certified lumber. There's other stuff about sustainable forestry here. There's the various lumber entities across the North America and how they grade things differently. There's different lumber grading systems depending which organization your lumber supplier belongs to. And such here. There's the timber construction. We're going to start getting into timber next. And there are engineered wood associations. So there's all these organizations that you actually can join, sign up for their newsletters, and get all kinds of interesting stuff from, depending on what you're thinking about specializing in for your career, So wood is one aspect. If you're going into the commercial business, you're not going to use a lot of wood. It's mostly residential, but it can be commercial on the apartment side, especially for 2 or 3 story buildings, that even though they're on the IBC we use. There's some more stuff about the plywood panels and very other kinds of panels and hardwood panels and that sort of thing. And chemical treatments. So I just went all out here this time. Okay. So we're ending with one more fun little picture here. This is a wood-made aircraft. This is a military. It was built to be a military aircraft near the end of World War II by Howard Hughes. And so Howard Hughes was getting a little nutty. It tends to happen to rich people. And he was very rich and powerful at this point. And he was just nut. He had a lot of psychological issues, but it doesn't mean he's completely nuts. Lots of nutty people are somewhat functional. Okay, well, I digress. He built this giant plywood and wood aircraft to prove it could be done, really, because everybody said it couldn't. And so this thing is massive and huge, and it's made of wood. It's got 1, 2, 3, 4, 8 engines on it. And you can see people standing at the top here. And anyways, they nickname it the Spruce Goose. I think it only flew once, and so he proved it did fly. But then it was in a warehouse forever, and now it's in a museum all around the Seattle area, around same area as Boeing aircrafts were at. But very impressive structure. So from that, I think we can call it a day and end the chapter on wood. But we'll have a math recording coming up soon. I'm going to develop and create and post dealing with the math for chapter 3 on wood, dealing with the board feet measurements, and then also for chapter 2 where we've got to deal with some volume questions of several different kinds.